In this tutorial, we will be discussing the quantum mechanics in the atom, specifically the Schrodinger equation and where the electrons are found. Using mathematics and probability, Schrodinger applied the idea of electrons behaving as a wave to the problem of electrons rather than as particles. He developed the wave equation, and you'll see this symbol here come up several times, and this is psi. It's the Greek letter psi. And so you'll hear it inadvertently from your instructor or throughout this video, and it's referring to Schrodinger's equation of the electrons behaving as a wave. This solution gives a set of mathematical expressions called the wave functions. Once again, there's that psi. Psi describes the area that the electron can be found in relationship to the nucleus. Psi does not denote the exact location of the electron in an orbital. Psi squared only gives the probability of knowing the location of the electron. So not the exactness, but the probability, the likelihood. Solving psi results in foreign values called the eigenvalues. These are the quantum numbers, and you'll find a tutorial later on that explains how to solve for each of these. N is the energy level. That's how far away it is. L is the shape dependent on the probability of finding the electron. N sub L is the orbital amongst the shape. And M sub S is what we're going to be discussing in the next tutorial when we discuss all of them at once. I don't want to overwhelm you. So what does quantum mechanics tell us about the atom's electrons? Well, it tells us that it's the wave nature, not the particulate characteristics of the electron that explain the chemical and physical properties. So this is all referring to the wave properties of the electron. The electron no longer is viewed as a small piece of matter orbiting around the nucleus, but as a cloud of probability. Remember, probability is the likelihood that is spread out over the orbit area. Now, Heisenberg's uncertainty principle. You probably have heard this term a lot in media, like movies. However, a lot of times they get it wrong, so let's make sure we understand it. Why the wave-particle duality nature of the electron makes it difficult to know its exact position and velocity it is traveling around the nucleus. Heisenberg explains that if you know where it is, it's impossible to truly know the velocity. If you know the velocity, it's the positions that's uncertain. So let's rephrase that. If you know the position, the velocity is uncertain. If you know the velocity, the position is uncertain. So you can know how fast it's going, but you can't know where it is. Or you can know where it is, and you can't know how fast it's going. You can only know one of the two. An electron's energy can be defined with exactness, but its exact position relative to the nucleus is known with limited certainty. We can only know the probability. And this is what the probability density function is. The probability of the density function represents the total probability of finding an electron in a particular area. So if we look over here, you'll see all kinds of scattered dots. Where you'll see the most dots are in the center, and that's where you get the greatest probability. There are a few on the outside here, but there's a lower probability of finding it there. And that's what this graph is showing us. R is for the radius. Side square is the probability. As you get closer to the center of the atom, the probability goes up, and that's why it's darker over here. Now, take a step back and look at the whole picture. This is the s orbital. 1s. 1 is the first energy level, so it's the first ring around the nucleus. S is the shape. That's the L. If we look at this, it looks like a sphere. Well, every energy level N has an s orbital. S orbitals have the lowest energy within the principal energy level N. S orbitals have a spherical probability plot, so that's why it's a circle here. So if we look at multiple energy levels, this is 2s, meaning the first energy level, the second energy level 2, and then L is the S. L is 0. The third energy also has an S, so N is equal to 3, and then L is equal to 0. Let's take a look at these pictures a little bit closer. Here is the 1s, and it's the dark, and that's really dark. And then you have the 2s out here. You have a white space in between. Well, if we look at our graph, there's a high probability of finding the electron, and then it drops, and then it goes back up, and then drops back down. Here, goes up, and down. This is for the third energy level. Here's the first energy level, 1s. This is the second s. Here's the third s. There's a blank area here because that is called the node, N-O-D-E. And that's where the probability drops to 0. Notice that for every energy level, it encompasses the ones in the inside. These are the p orbitals. So once again, we're still looking at the quantum number L, but notice that there's 3 of them here. There's one here, and one here, X, Y, and Z. And that's what we mean when we say M sub L. It's describing it in the individual orbitals. And then here's D. There's 5 of these. So D is the L, and then M sub L would be all these individual orbitals. And that gives you an introduction to quantum numbers, including energy level, the shape, or the L, quantum number L, and the quantum number for M sub L for the specific orbital.